Welcome to this coding walkthrough. In this session, we will explore an interesting problem titled Index Pairs of a String. We'll break down the problem statement, discuss possible approaches, and analyze the trade-offs. Let's get started. This problem is about finding specific substrings within a given string. You are provided with a string called text and a list of words called words. The task is to identify all substrings in text that match any word in words. For each match, you need to return the starting and ending indices of the substring as a pair, I, J. These pairs must be sorted in lexicographical order, meaning they are ordered first by the starting index, and if two pairs share the same start, by the ending index. The input consists of the string text and the list words, while the output is a list of index pairs. Let's look at some examples to better understand the requirement. In the first example, the input string is the story and the list of words is, the story is. The output is 0, 2, 3, 7. Here, the word the is found in text starting at index 0 and ending at index 2, while the word story is found starting at index 3 and ending at index 7. The word is does not appear in the string, so it is ignored. Notice that the output pairs are sorted lexicographically. Now consider another example where the input string is ababa and the list of words is aba, ub. The output for this example is 0, 1, 0, 2, 2, 3. Here, the word ub is found twice, once at indices 0, 1, and again at indices 2, 3. The word aba is found at indices 0, 2. The output is arranged in lexicographical order, with the smallest starting index first. Now, let's look at another example to solidify our understanding. If the input string is Mississippi and the list of words is, sip, miss, the output is as follows. The result is 1, 2, 4, 5, 6, 8, 0, 3. In this case, the word is appears twice in the string, at indices 1, 2, and 4, 5. The word sip is found at indices 6, 8, and the word miss is found at indices 0, 3. Just like before, the output is sorted in lexicographical order. It's important to always ensure the pairs are returned in the correct order. To fully define the problem, let's review the constraints and edge cases. The constraints specify that the length of text can range from 1 to 100 characters, while words can contain up to 20 strings, each up to 50 characters long. Both text and words consist only of lowercase English letters, and all words in the list are unique. Some edge cases to consider include when no words from the list exist in the string, such as when text is ABC and words is XYZ, which results in an empty output. When matches overlap, such as in ababa with words being ABA hub, all valid pairs are included. Lastly, ensure the output is always sorted lexicographically, with the primary order determined by the starting index and the secondary order by the ending index. For example, given cabin words as A, B, C, the output would be 0, 0, 1, 1, 2, 2. To begin solving the problem, we can consider a brute force approach. The intuition here is straightforward. We check every possible substring of the input string text to see if it matches any of the words in the words list. Specifically, we iterate through all possible starting indices of text and, for each starting index, iterate through all possible ending indices. For each pair of indices, we extract the substring and check if it exists in the words list. If it does, we record the starting and ending indices as a pair in the result. However, this approach is computationally expensive. The time complexity is proportional to the square of the length of text, multiplied by the average length of the strings in words due to the repeated substring extractions and comparisons. While this method is easy to implement, it becomes highly inefficient as the input size increases, making it impractical for larger inputs. Additionally, it does not take advantage of any structure within the words list to optimize the matching process. A more efficient solution involves using a tree, also known as a prefix tree. By storing all the strings from the words list in a tree, we can perform faster substring checks. The process begins by constructing the tree, which organizes the words in a hierarchical manner based on their shared prefixes. Once the tree is built, we iterate through each starting index of the string text and attempt to match the longest possible substring beginning at that index. The tree allows us to progressively check each character, stopping as soon as no further matches are possible. If a match is found, we record the corresponding index pair. This approach significantly reduces redundant comparisons because it avoids rechecking overlapping substrings. The time complexity is linear with respect to the length of text, multiplied by the average length of strings in words, making it far more efficient than the brute force method. However, it does require additional space to store the tree, which is proportional to the total number of characters in words. Despite this trade-off, the tree-based method is well suited for larger inputs, where efficiency is critical. Another alternative is to use built-in string matching functions, such as Python's strfind. For each word in the words list, we search for all its occurrences in the string text. Whenever a match is found, we record the starting and ending indices of the substring. Once all the matches have been collected, the resulting index pairs are sorted in lexicographical order. This approach is relatively simple to implement and leverages the optimization of built-in substring search algorithms. However, it has its limitations. The repeated searches for each word can result in slower performance compared to the tree-based approach, especially for larger inputs. Additionally, sorting the result introduces extra computational overhead. While this method can be effective for smaller datasets or scenarios where simplicity is prioritized, it is not as scalable or efficient as the tree-based solution when dealing with large input sizes. Among the approaches discussed, the tree-based solution stands out as the most robust and scalable. It avoids redundant substring comparisons by leveraging the hierarchical structure of the tree, which groups common prefixes of the words list. This design ensures efficient substring matching, even for large input sizes. Furthermore, by traversing the string text sequentially, the index pairs are naturally processed in lexicographical order, eliminating the need for additional sorting. Key insights that make this approach effective include the ability to stop early when no further matches are possible from a given starting index and the way the tree minimizes unnecessary work through its structure. While this method requires extra memory to store the tree, the trade-off is justified by the significant reduction in computation time. In contrast, the brute force method is only suitable for small test cases, and the string matching approach, though simpler to implement, does not scale as efficiently. Overall, the tree-based solution strikes the right balance between performance and scalability, making it the optimal choice for solving the index pairs of a string problem. To approach this problem, the brute force solution starts with iterating through all possible starting indices of the string text. If the string has a length of n, then the outer loop will consider indices from I equals 0 to I equals n1. Each starting index represents a potential beginning of a substring. Within this outer loop, we then iterate through all possible ending indices to form substrings. For each starting index I, the inner loop goes from j equals I plus 1 to j equals n, where j denotes the endpoint of the substring. The substring formed will be text, i.e. j. Once we have the substring, we check if it exists in the given list of words. This check can be done either by directly comparing the substring with every word in the list, or by using a pre-computed hash to speed up the lookup process. This method ensures that we systematically explore all possible substrings in the text to identify matches. Now, when a match is found, the next step is to record the result. This could involve storing the matched substring, its indices, or any other relevant information in a suitable data structure, such as a list or a set. After processing all possible substrings for a given starting index, we move on to the next starting index and repeat the same process until all indices in the string have been covered. Finally, after processing all possible starting positions, we return the required output. This could be a list of all matched substrings, their positions in the text, or any other format specified by the problem requirements. By following these steps, we ensure that the brute force approach systematically evaluates every possible substring for matches. This approach, while straightforward, has significant computational costs. The time complexity of iterating through all substrings is n squared, as we evaluate every possible start and end index pair. For each substring, checking against the list of words takes m, where m is the size of the words list. This makes the overall time complexity n squared * m. Additionally, if we store the matched substrings, the space complexity depends on the number of matches, which in the worst case can be n squared. There are also edge cases to consider. For example, if the input text or words is empty, the solution must return an appropriate result, such as an empty list. Overlapping matches may require special handling, depending on the problem's requirements. Case sensitivity and special characters in the input are other factors that might need to be addressed, ensuring the solution is robust and handles all possible scenarios correctly. The choice of data structures plays a critical role in implementing and optimizing this algorithm. First, the words list is essential as it holds the words to be matched against. While a simple list works for brute force, using a hash-based structure like a set or dictionary can significantly speed up lookups. For storing the matched substrings, a result list or set is commonly used. A set is particularly useful if duplicates need to be avoided, while a list can be used if duplicate entries are allowed. Additionally, a hash map can be employed to store pre-computed hashes of the words and substrings. This allows for faster comparisons during the matching process, reducing the time spent on direct string comparisons. By carefully selecting the right data structures, we can make even a brute force approach more efficient and manageable. To further enhance the algorithm, several optimizations can be implemented. First, redundant comparisons should be avoided. If a substring text, ij, is found not to match any word, there's no need to continue evaluating similar substrings that share the same base. Hashing can also play a critical role in optimization. By pre-computing hashes for all words in the list and comparing those with hashes of substrings, we can replace expensive string comparisons with faster integer comparisons. Another useful technique is the sliding window approach. Instead of repeatedly creating new substrings, we can dynamically maintain and update the current substring as the window slides across the text. This minimizes redundant operations and reduces the overhead of substring extraction. Incorporating these optimizations can significantly improve the efficiency of the algorithm, making it more practical for larger inputs. The provided Python implementation solves the LeetCode problem number 1065, index pairs of a string. The goal is to find all start and end indices of substrings in a given string text that match any word in a list of words. These indices are returned as pairs in a sorted order. ### explanation of the code. 1. Initialization asterisk. The function index pairs takes two inputs, text, the main string, and words, a list of substrings to look for. It initializes an empty list result to store the index pairs. 2. Iterating over words asterisk. The function iterates over each word in the words list. Each word is treated as a potential substring to find in text. 3. Finding all occurrences asterisk. For each word, the function uses Python's strFind method to locate the first occurrence of the word in text. If a match is found, it records the starting index, start, and calculates the ending index using the length of the word, start plus word underscore len1. The pair, start, end, is added to the result list. Using a while loop, the function continues searching for subsequent occurrences of the word by calling text.find, with an updated starting position, start plus 1. The loop exits when no more matches are found, find, returns -1. 4. Sorting results asterisk. Once all words have been processed, the result list may contain pairs in an unsorted order. To ensure the output meets the problem's requirements, the function sorts the result list by the starting index, and by the ending index if two pairs share the same start. 5. Returning the result asterisk. Finally, the sorted result list is returned. ### edge cases. If words is empty, the function returns an empty list immediately. If none of the words in words match any substring in text, the result list remains empty, and the function returns an empty list. The function handles overlaps correctly by using text.find, iteratively for all occurrences of each word. ### complexity. Time complexity asterisk for each word, the find operation scans through the text, resulting in a worst-case complexity of O, k asterisk n, where k is the number of words and n is the length of text. Space complexity asterisk the space usage is dominated by the result list, which stores up to O, k asterisk n, pairs in the worst case. This implementation is efficient and adheres to the problem's constraints, ensuring correctness and clarity. This is the Java implementation of LeetCode problem number 1065, index pairs of a string. It mirrors the logic of the provided Python solution, using Java-specific constructs such as ArrayList for dynamic storage and arrays.sort for sorting. The function iteratively finds all occurrences of each word in the given text, storing the start and end indices as pairs. The result is then sorted based on the problem's requirements and returned as a 2D array. Key differences from Python include explicit type declarations and the use of Java's collection framework for intermediate storage. Here, we start with a basic example where the input string is the story of LeetCode and the list of words contains story, leet, and code. To solve this, we initialize an empty list called result to store our index pairs. Then, for each word in the list, we begin searching for its occurrences in the text. Starting with the word story, which has a length of 5, we find its first occurrence at index 3 using the find method, and calculate its ending index as 7. This gives us the pair 3, 7, which we add to result. Since there are no further occurrences of story, we move to the next word, leet. For leet, with a length of 4, we find it starting at index 10 and ending at index 13, so we append 10, 13 to result. Again, there are no additional occurrences. Lastly, we process the word code. For the word code, which has a length of 4, we locate its first occurrence at index 14. The ending index is calculated as 17, so we append 14, 17 to the result list. With no further matches for code, we complete the iteration over the list of words. At this point, the result list contains the pairs 3, 7, 10, 13, 14, 17. To ensure the pairs are sorted in ascending order, we sort the result list, though in this example it's already sorted. Finally, we return the sorted result, which is 3, 7, 10, 13, 14, 17. This output represents all the index pairs where the words appear in the text. Now let's consider a more complex example where the text is ABABA and the words are ABA and BA. We initialize an empty result list as usual and start iterating through the words. First, we examine the word ABA, which has a length of 3. Its first occurrence is at index 0, giving us the pair 0, 2, which we add to result. Searching further, we find another occurrence starting at index 2, ending at index 4. This results in the pair 2, 4, which is also added to result. With no additional occurrences, we move to the next word, BA. For BA, which has a length of 2, we find its first occurrence at index 1. For the word BA, the first pair we form is 1, 2, which we add to result. Looking further, we find another match starting at index 3, creating the pair 3, 4, which is also added to result. At this point, there are no more occurrences of BA. The result list now contains the pairs 0, 2, 1, 2, 2, 4, 3, 4. To ensure the pairs are in ascending order, we sort the list, resulting in 0, 2, 1, 2, 2, 4, 3, 4. This sorted list is returned as the final output. It represents all the overlapping and non-overlapping occurrences of the words within the text. Next, we'll look at an example where no matches are found. In this final example, the text is hello and the list of words contains world and leet. We begin by initializing an empty result list as usual. For the word world, which has a length of 5, we try to find its first occurrence in the text, but find returns -1, indicating no match is found. Similarly, for the word leet, which has a length of 4, no occurrences are found in the text. Since neither word is present in the text, the result list remains empty throughout the process. With no index pairs to sort, we directly return the empty result list as the output. This demonstrates how the solution handles cases where none of the words appear in the text. This solution analyzes both the iteration over the words list and the process of searching for each word in the text. First, we have the outer loop, which iterates through all the M words in the words list. Each word is processed one by one. For the inner loop, we use the find method to locate all occurrences of a given word within the text. Here, the worst-case scenario occurs when the find method needs to scan the entire text, which has a length of n. If a word appears multiple times, the total number of searches performed is proportional to its frequency. After gathering all the index pairs, the algorithm sorts the result list, which consists of p pairs. Sorting this list requires p*log, p time, meaning the sorting step further contributes to the overall complexity. To summarize the total time complexity, the worst-case scenario involves scanning the entire text for each of the M words, resulting in O, M asterisk N. Additionally, the sorting step adds O, P asterisk log, P, making the total time complexity O, M asterisk N plus P asterisk log, P. For space complexity, the main consideration is the result list, which stores all P index pairs and requires O, P, space. The rest of the algorithm uses only a few variables, such as start and word underscore len, which require constant space, or O1. Combining these factors, the total space complexity of the solution is O, P, where P is the number of index pairs stored in the result list. Now, let's break the analysis into best, average, and worst cases. In the best case, if the words list contains very short words, such as single characters, and these characters are rare in the text, the number of searches is minimal. This keeps the time complexity close to O, M asterisk N. In the average case, if words contains words of moderate length and these words appear with average frequency in the text, the complexity remains O, M asterisk N plus P asterisk log, P. For the worst case, when words contains long words that occur frequently in the text, the find method may need to perform multiple full scans of the text. Additionally, sorting a large result list in this case contributes significantly to the time complexity, which remains O, M asterisk N plus P asterisk log, P. A comparison with a brute force approach highlights the efficiency of this solution. In a naive approach, we would generate all possible substrings of text and explicitly compare each one against all words in words. This would result in a time complexity of O, M asterisk N squared, as generating all substrings alone requires O, N squared. However, the provided solution avoids this inefficiency by leveraging Python's optimized find method, which eliminates the need to explicitly generate substrings. The big O proof confirms the efficiency of the solution. Each find call scans up to N characters in the worst case, leading to O, M asterisk N, for all words, while sorting the result adds O, P asterisk log, P. Combining these terms, we achieve the overall complexity of O, M asterisk N plus P asterisk log, P, which is significantly better than the naive alternative. When working on string problems like this, there are a few common mistakes to watch out for. First, not accounting for edge cases can cause major issues. For example, if you overlook cases like an empty string or very small input sizes, it could lead to runtime errors or incorrect results because your code might not handle these situations properly. Another frequent mistake is using inefficient methods for substring checks. If you rely on nested loops to scan for substrings, you might inadvertently increase your time complexity to O, and superscript 2, whereas a more optimized approach like a sliding window or hash map can reduce it to O, N. Overlapping substrings are another tricky area. If you fail to account for regions in the string where multiple matches are possible, important results could be missed. Lastly, in optimized approaches like sliding windows, mismanaging pointers can lead to skipped elements or even infinite loops if you move them incorrectly without ensuring all conditions are satisfied. Another common pitfall is assuming input constraints without properly validating them. For instance, if you assume that all strings only contain lowercase letters without verifying this in the problem statement, your solution might behave unpredictably or crash when faced with unexpected inputs. Now, when it comes to interviews, there are some key strategies to keep in mind. Recognizing patterns is crucial. Techniques like sliding windows, hashing, and prefix sums often appear in string problems. Developing a strong intuition for these approaches will help you solve problems more effectively. Additionally, always ask about edge cases during interviews. Think about scenarios like empty strings, single character strings, or extremely large inputs, and clarify these with your interviewer. A good practice is to start with a brute force approach to ensure correctness and then optimize step by step, explaining your thought process clearly. Be mindful of space-time trade-offs, such as using a hash map for faster lookups at the cost of higher space complexity. Finally, after writing your solution, walk through a few test cases, including edge cases, to verify that your code works as expected. To deepen your understanding, it's helpful to explore related problems that involve similar techniques. For example, problems like LeetCode 76, minimum window substring, LeetCode 3, longest substring without repeating characters, LeetCode 567, permutation in string, and LeetCode 438, find all anagrams in a string, all share overlapping concepts. Studying these can improve your grasp of string manipulation and pattern matching. Now, there are also alternative approaches to solving these types of problems. The sliding window technique is a powerful method that reduces time complexity to O(n), but requires careful management of pointers to avoid mistakes. This approach works particularly well for problems involving contiguous substrings or patterns. Another option is leveraging hash maps or sets for lookups, which significantly improve the efficiency of existence checks or uniqueness validations. However, this approach comes with the trade-off of increased space complexity, so it's important to weigh the pros and cons based on the problem requirements. Another alternative approach is to use prefix sums or prefix arrays. These are especially useful for problems that involve cumulative frequency checks or segment-based queries, as they allow you to pre-process data for faster lookups during the main computation. However, prefix sums can sometimes be overkill for simpler substring problems, where a more direct approach might suffice. The key is to understand the trade-offs and choose the method that best aligns with the problem's constraints and goals. By mastering these techniques and knowing when to apply each one, you can tackle string problems with greater confidence and efficiency. Great job sticking through the problem. We've explored the index pairs of a string challenge and walked through the intuition, algorithm, and analysis. Remember to practice these concepts to strengthen your problem-solving skills. Thanks for watching, and I'll see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!